Hello students, how are you? I hope you all are doing great at home and doing your research. So here we are going to discuss on your project 2020. So first we are going to the next topic, this one. Here we know that you have you have the titles. We have three groups. One is for BSc, the rest two are of MSc. I named the groups as A and B. In Group A, those Group A consisting of Rafiqul, Nilima, and Meenakshi, whose title of the project is Generation and Propagation of Soliton in Quantum Well Nanostructures. And in Group B, consisting of Noor Alam, Jakam, Marak, and Ingam Kena, and they are having the title of Investigation of Nonlinearity Induced Self-Phase Modulation in Quantum Well Nanostructures. So we are going to discuss these two MSc projects today. Here we see uh, we are going to discuss these two uh, projects. For Group A and B, Group B. So their target is nonlinear Schrodinger equation. Already we have from our calculation we have reached the nonlinear Schrodinger equation. This is of this kind. Let me take this screen myself here. So in this equation, I hope probably you already have come across this equation. Here in this equation, this is nonlinear Schrodinger equation, and here three main parts are there. The first part is yes, the first part is pulse form, which gives uh, the the form of the pulse, means the spatial distribution of the pulse that we are going to use. The second part is uh, containing three terms: one, the second, third, and fourth term. These are higher order dispersion terms, and the third one is nonlinearity terms. So, what is there in this pulse? This pulse deals with the pulse form, the spatial distribution of the pulse, then the dispersion part, which is a linear factor. The this dispersion, this the higher order dispersion, what it gives the how it gives the information how the pulse will be propagating through the nonlinear system, means how it will be dispersed through a nonlinear system if the system is nonlinear and dispersive. The third term gives the nonlinearity. The last term gives the nonlinearity. Now, in this part, we already know that nonlinearity induces many nonlinear effects like self-phase modulation, cross-phase modulation, four-wave mixing, etc., etc., solitron generation, etc. So, this term, the nonlinear term, is responsible for those things. Now, we will be discussing step by step. Here, our target is there are two targets. One is for Group A. We need to discuss. We need to discuss how the soliton will be generated and propagated. Okay, and second Group B, we will be discussing how this nonlinearity will be inducing the self-phase modulation into the nonlinear medium. Here in our projects, we are taking the quantum well nanostructures is our nonlinear medium. So that is a very small, tiny uh, quantum well system, and because of that quantum well, that tiny quantum well system, the solid base system, we can almost take the dispersion, the attenuation we can take 0. So we will have this alpha exponential term will be 1. Okay. So next, coming to the topic is we need to now the evaluate the beta 2, beta 3 and beta 4. These are the second order, third order and fourth order dispersion term appearing in the nonlinear Schrodinger equation. You can see in the higher order dispersion terms there are beta 2, beta 3 and beta 4 terms are appearing. Now we uh, need to calculate those beta 2, beta 3, beta 4, and also what is the W. We need to evaluate these 1, 2, 3, 4 parameters for a set of values delta P and delta omega C with other system parameters, as we have already discussed, and we have found our system parameters, and also we need to find with that system parameters we need to find those values beta 2, beta 3, beta 4, W uh, for a particular set of parameters. Now here I'm giving an example. Say for example, if our system parameters are these, this n is the number of atoms, sorry, number of electrons present in the quantum well system. Omega 1 2 is the dipole moment of that quantum well system that we have taken. Omega p is frequency, pro frequency. Delta p, here delta p is important. We already have plotted the susceptibilities with respect to uh, this probe detuning. Delta p is a probe detuning. So uh, we have taken the probe detuning for up to a certain point. Say for example, we have taken the probe detuning uh, plus minus 5% of the profile. So here uh, the probe detuning, say for example the probe detuning is from 2 into 10 minus 2 into 10 to the 12 to plus 2 into 10 to the 12, right? So that is our bandwidth that we are searching. We are checking what is the behavior of this susceptibilities. Okay. Now we need to select a frequency of that within that limit of delta p ranging from minus 2 into 10 to the 12 to plus 2 into 10 to the 12 second inverse. Within that limit we have to check one particular frequency. Say for example, here we are checking delta p equal to 0.2 into 10 to the 12 second inverse. Okay, very near to the 0 point and towards positive. Okay, this is a positive quantity of delta p. Now at that point we'll be searching what will be the values of beta 2, beta 3, beta 4 and W. Okay, and we have taken delta C probe control detuning 0, delta P, that this should be delta C, sorry, omega C. The omega, capital omega P should be a capital omega C, that is a mistake. So let us take omega C, capital omega C is 4 into 10 to the power 12 second inverse. That is just an example, okay? And other two parameters, system parameters are there, the gamma, the gamma 31 and gamma 21, which are the dephasing parameters. Okay. Now uh, uh, let us consider let us consider that these are the values of the nonlinear Schrodinger equation, the terms appearing in the nonlinear Schrodinger equation. There appears a kappa that from your equation you can have the value of kappa, because this kappa is appearing will be appeared in the expression of W. So that will be also counted, that will be a constant. So here we have taken the beta 2, here it is written beta double dash, means beta double dash and beta 2 both are same. Beta double dash, beta triple dash, beta 4 dash. So these are betas, beta 2, beta 3, beta 4, etc. Okay. Then again we have calculated W. So and also chi 1 and chi 3. Here you can see that we have already written that the values of beta 2, beta 3, beta 4 and W will have two parts, real and imaginary, and the real part must be at least 10 times larger than the imaginary part. Okay, so here you can see that beta 2, here you can see this is 1.45 and this is the first part is real part, the second part is imaginary part. Now if you consider that this is 1.45 and this is 0.68, so definitely the real part is 10 times, almost 10 times larger, that because this decimal point is uh, below 0, after 0. So similarly for beta 3 also, this is 1.5, real part is 1.52, imaginary part is 0.82. So that is imaginary part is smaller than the real part. Similarly for all these things you can see chi1 and chi3 I have just taken a random value. This is not for particular for your calculation. Okay, you will be calculating by yourself, okay, for your own system. Here chi1 also, it will be the real part will be larger than the imaginary part. Chi3 also, real part will be larger than the imaginary part. Why we are doing so? Because in most of the cases we have to take the real part, the imaginary part we will be dropping. Okay, so if imaginary part is larger, then we cannot drop. So your real part of all these terminal, all these terms, all these parameters, like beta 2, beta 3, beta 4 or W, in this all these cases, beta, the real part should be taken and imaginary part should be neglected, and that we can do only one case, if imaginary part is smaller than the real part. Okay, so we are coming now to the next part, what we are going to do. Another thing here we must check, we must tell that here you can see, here you can see we have beta 2, our main target is beta 2 and W. Here W is negative, you can see in the values, W is negative. Let us take only the real part, negative 2.85. Then beta 3, sorry, beta 2 is 1.45 positive. So these both term will be positive. In that case, one thing will be there, if we have this kind of system, then this is negative. Okay, then the last one will be negative in nature, and definitely beta 2 is positive 1.45. So beta 2 will be positive if it is minus, in front there is a minus sign, so that will be negative. This is also negative, this is also negative. If both this sign before the beta 2 and W will be same, then there will be a problem for soliton generation. So we have to check at particular value uh, at which these two terms will be opposite in nature. So here you see, the if we have delta p is these terminologies are appearing because of at the point of delta p equal to minus 0.2 into 10 to the 12. So we will be changing it, delta p, we will change the delta p, then it will be again changed. These terms, values of nonlinear Schrodinger equation terms will be changed. Then we have to confirm at some certain point that at what point these two will be opposite in nature. Okay, so let's come to the part, come to the discussion, what this group A and group B has to do. For group A, to study the soliton of all three parts required. Yeah, this for to study soliton, all these three parts 1, 2 and 3 is required. TOD and FOD. TOD means third order dispersion, means this beta 3 part. FOD means fourth order dispersion, beta 4 part. May or may not be used. We can sometimes you can drop it for our